So previously we talked about PID controllers and how using root locus we design a PID controller, and we mentioned that to design a PID controller, these are the steps. We first turn off Ki and Kd, increase Kp until we get to the edge of instability, then start decreasing Kp to get quarter amplitude decay behavior, and then we increase Ki and Kd manually to achieve the desired behavior. And we showed for this example that Kp equals to 370, Kp equals to 370 gives us the amplitude, quarter amplitude decay behavior. Now we want to go to next step, that is Ki and Kd. Okay, obviously we have a lot of different values for Ki and Kd that give us the behavior that we want. So now we need to do some discussion. We need to have a discussion. If we decide to use Kd, we will have the root locus of figure 8. So let's look at figure 8. This is figure 8. If we use Kd, we are going to have this behavior. Therefore, we see that Kd will move complex poles to the left, right? So these poles are going to move to the left. And what that means is that increasing damping ratio will happen if I have a Kd, and therefore decreasing overshoot and settling time will happen. If alternatively, I set Kd equals to 0, but try to increase the value of Ki, we get this root locus. So now look at here. If we use Ki, with increasing gain a little bit, we can become unstable. So if we use Ki, we get the root locus of figure 9, which means increasing Ki will move complex poles to the right and increase overshoot and settling time. So imagine if the customer tells me we want a design to have settling time of 2.4 seconds and percentage overshoot of 12.8%. Then we can design Kp and Ki accordingly to get to that point, which means Kd would be 60 and Ki would be 100.